We're going to start posting each podcast episode that you see on YouTube a week earlier on Patreon. So feel free to join for early access to all episodes. Plus, we're going to start doing bonus podcast episodes every week. So if you want to join Patreon, it's patreon.com/concrete videos. Next week's episode is already posted there, so feel free to go check it out. Hello, world. Today, my guest is Mark Levinson. Mark is a trained particle physicist who got his Ph.D. from the University of California, Berkeley, before going to Hollywood as a sound editor on films like The English Patient, The Talented Mr. Ripley, the movie Seven, and House of Cards. On this podcast, we talked about his documentary Particle Fever, where Mark tells a story of the experimental discovery of the Higgs boson. The film covers the scientific process and the scientists behind the research with the Large Hadron Collider, which is the $1 billion piece of machinery in Switzerland that basically collides and smashes atoms together and shit like that. The film covers the scientific process and the actual scientists behind the research, and it documents the first time they discovered the Higgs boson. So without further ado, please welcome the amazing Mark Levinson. Thanks for coming on here, man. I really appreciate it.
Good. Well, looking forward to it.
The very last line of the Particle Fever documentary, where he says the most important things, the things that make us human, are the things that we don't depend on for survival. The things that humans don't need for survival are the things that are most important.
Yes.
That was a very profound statement he made there.
Yeah, I mean, the thing is, I mean, I've always been interested in the overlap between art and science. Sorry about that.
That's okay.
Let's see if I can just turn this off. I mean, for me, as somebody who started in, in the field of science, really, and, getting my doctorate in physics, and then moved into more of the arts with filmmaking, I never really made that distinction. People always ask about that. Oh, well, how did you make that? How did you make that transition? And in fact, it was something that I wasn't even aware of as a big transition. I mean, obviously in my day-to-day activities, in some sense it was, but it's not as if I felt like I have this part of my brain that is doing science and this part of my brain that's trying to do film. I mean, they're both creative, and I think they're both important. And so what Savas says there, I think, is reflective also of both frontier level scientific research and the arts. I mean, that these things that really distinguish us as humans, these abstract things that we pursue. I mean, why do we try to understand the universe? As I think he also says in the film, it's not something that's going to, for the most part, influence our day-to-day life or have a lot of practical applications, but we need to do this. And the same thing about art. I mean, you could say that, for a lot of people would question, what is the usefulness of this? Why do we do this? And the answer is that it's just, it's something that it's what makes us human. I mean, Fabiola talks about this too in the film. She has the Dante quote, that this is the thing that distinguishes us from beasts or other animals, that they don't paint and write literature and try to understand where they came from. So I was very happy that Savas came up with this. I mean, it was something I was interested in, but I didn't want to, just feed them the lines. And Savas, Fabiola, Nima, I mean, all of them, really felt the same kinship to artists and what they do.
What was it that brought you to make the decision that you wanted to go dive into this world, into the lives of these people who are creating this $1 billion machine that is, its purpose is to just smash atomic particles into each other? And how did this journey start for you to create this thing?
Well, I mean, the journey actually started in college when I got interested in physics. And so I originally was going to college. I thought I was going to be an MD. And so I actually was in a program, it was a special program that was a combined MD PhD program. And I thought I'd get an MD and I thought I'd study, and then I'd do research and I'd sort of do a combination. But it was sort of the quintessential story of an incredible professor at college who was this brilliant physics teacher. And I decided to take the physics major's physics course because also I just sort of wanted to be away from the pre-med rush where most of the pre-med people are just taking physics because they have a requirement, and I was interested in it. So I thought, okay, I'll take the physics majors one. I was good in math and science, and the guy walked in the first day and he picks up this huge book and he says, "This is a book," but he tosses it across the room. He says, "But we're not going to care about books. We're interested in learning how things work and learning how the universe works." And I thought, wow, sign me up. Especially in contrast to a lot of the pre-med stuff where it was really about memorization and learning things like that. And I think I was just really fascinated by the search for fundamental truth and understanding. I mean, that's what I was interested in physics. And I really got drawn to the most theoretical physics and the most fundamental physics. And so particle physics is, in a sense, it's the ultimate physics. I mean, everything ultimately comes down to what are the fundamental particles of the universe and what are the forces and how do they interact. And essentially everything comes from that. And that was very appealing to me. I mean, to try to understand, just if you want to understand the universe, that's the most fundamental level that you can understand it. And so that took me through college and through graduate school. So it was, I was studying this field, but at the university, I did begin to see other, the other things. I was sort of awakened to film and to literature, and I think it was particularly actually a lot of Eastern European cinema that I saw that was very complex, intellectually challenging, and trying to understand the universe also, but from the more humanistic perspective. And so that's the other thing is I saw film as another way of trying to understand the universe. And physics, you were looking at it from the aspects of the physical components like particles and forces, but film I saw as a way to also examine how the universe works from a human perspective. And there's a number of parallels, I think, but between the two, that for me a script in some sense is like a theory. A film for me, is something that is a representative of something of the world, some truth that is in a compressed form. I mean, at least for me, the greatest films are. They're saying something. They contain some sort of truth in a compressed form, which is like a theory in physics, actually. That you look for a theory that is a simplification of things, but is also representative of much broader things. And you look for again a sort of a simplification, an essence of things that has a broader significance, and even in process in a certain way. In science, you look at you have a theory of something about how the universe works, and in film, you start out with a script of some idea of something that you're trying to investigate, and then in physics, you go off and you do an experiment to test it, and you are suddenly the experiments are often really huge and expensive, and you hope you get something useful. And in film, you go off and you make the film. And again, it's suddenly very different from the more solitary process of writing or coming up with a theory. But you go out, you have a crew, do this incredible, crazy thing, and you hope you get something useful. You hope you get some useful data. And then in physics, you go back with the results to your theory, and you say, oh, okay, what it really is? What is the real world like? And in film, you get the footage back into the edit room, and you sort of say, oh, that's what my film is about. It may be very different. So there's certain parallels in that regard, actually, too, in terms of the steps. So when I got my PhD, I really did get interested in exploring this other way of looking at the world from the humanistic perspective. And I actually went into narrative film. I mean, what I described is really the path for a narrative feature, where you have a script and then you shoot and you go to the edit room. And I actually had nothing to do with science. I mean, so my foray into film for many years was in the narrative world. I wrote a script about former Russian dissident artists dealing with all the changes after Glasnost. Again, I was so fascinated by art and artists and what they were doing. And so I worked in that field. I wanted to do more writing and directing. I began to specialize in post-production and working with actors to redo lines and to change lines and something that's called ADR, right, or looping, and then alternately working on my own things. But I was always thinking that I wanted to do something that try to perhaps connected the strands of my life. And I was thinking about a script, possibly writing a script that looked at sort of science in a very realistic way. I mean, I didn't feel, and still don't feel, that there's a lot of fiction films that deal with science, in a very authentic way. And so I was thinking about that, and then I heard about this physicist, David Kaplan, who he was trying to make a documentary about the startup of the Large Hadron Collider. And the Large Hadron Collider was the experiment that was designed to test the fundamental theories of particle physics, which is exactly what I had been studying in graduate school. So it was something where I could recognize very much the issues, the stakes, and I knew what was involved, what people were looking for, and how long they'd been looking for it. And so I could sense that if this thing was really finally about to turn on, it could be a dramatic film. And so I told David that I was not interested in doing a straightforward science documentary where we're just going to try to explain particle physics, but that if I could use my filmmaking tools to make it about characters and make it, try to make it follow a narrative, that would be really interesting, and I could see the potential. And he agreed, and so I jumped in. And so it presented this opportunity to sort of combine in my mind these two strands of my life, two strings in some sense, of physics and film and narrative and story. And that's how it came about. And of course, it ended up being much more dramatic than we expected. I mean, when I started, most of the physicists said they probably wouldn't find the Higgs boson while we were filming. I was trying to think of various dramatic scenarios, thinking in terms of story, what it could be. I had various ideas of, how I could set it up, and, what we might do in terms of, different, different teams competing, or the difference between theorists and experimentalists, which was something that was very interesting to me, and something I think was not so well known outside of the field, outside of what happens in a lot of science, but it's really accentuated in physics, because the experiments like the Large Hadron Collider are so enormous and, so time consuming. And, so I was thinking about those distinctions, and, we were very lucky that they did end up discovering it while we were still filming. So
why does that thing have to be so enormous?
Well, it is an irony that, you're studying the tiniest things in the world. Right. But um, in order to study them, you need incredibly high energies. And we get high energies by accelerating these things around and around, and you need a certain distance, in a sense, to build up the speed. Also, to keep particles, to keep charged particles, this is accelerating protons, which have a positive charge, to keep them going around in a circle, you need very, very strong magnetic fields. And the tighter you try to bend them, the stronger magnetic field you need. So there's a certain size requirement you need to, in a sense, to get them faster. So, the faster you want to make them curve around, the stronger the magnets you need. And, there's a trade-off. And the energy you need to basically keep them in track, and the energy that is in them to combine and create something. And the fact is, we're looking for particles that are very massive, that have a lot of mass. And by Einstein's famous equation, E equals mc squared, E is energy, is proportional to the mass. And so to get higher mass particles, you need higher energy. You need higher energies that you're creating, that basically you're putting energy in, this movement energy, and crashing them together, and you want to transfer that energy of this motion into the mass of these particles. So you need this huge thing to build up enough energy to create massive particles. And the size also is determined by by the energy that you need to get, and how do you keep these things going. I mean, it's a phenomenal technological feat when you think about it. That I remember, I think I saw something that said, getting these things, because you're accelerating protons, and that it'd be like firing a gun from here and from the moon, and you're having the bullets collide. I mean, that's almost the accuracy that you need. So it is pretty astonishing that it actually works.
Yeah, it's extremely mind-bending how the scale and the enormity of that thing. So there's 4 different chambers within that 17-mile loop where the particles actually collide. Why do those chambers? Can you explain what the significance of those giant chambers are, and why they have to be 5 stories to? It's basically like I think they described it in the documentary as a 5-story camera lens.
Yeah, right. Yeah. So the Large Hadron Collider itself is this ring of basically two tunnels of protons that are sent circulating around in opposite directions. So they're sent around, and they get faster and faster and faster. And then these 2 beams are, crossed. So the beams are directed towards each other, and they cross at 4 points where you can have the collisions. Okay. And the collisions, again, you're slamming things together, each of them going very fast. You're getting the highest energy. When these particles collide, lots of things come out. So it's the combined collision, the mass, the energy is converted into mass that flies off into various different particles. And so what you want to do is you want to see what they are. So they go flying off in all directions. And the experiments, so what are in these different chambers, are 4 different experiments. And they're completely different teams of people. They work independently. They are designed to detect different things. You can try to detect different things, and you can set it up in different ways. And so essentially they're layers, because as things come out, you can slow things down in some ways, and you can measure the speed and the energy of the things. You put in your own magnetic fields, and you can see these particles, then charged particles will curve in these things, and by the angle of the curve, you can determine things about their mass and other internal properties, with their magnetic properties and things like that. And so you have these layers also to stop different particles. Different particles are going to get stopped at different places. Different layers are going to detect different properties. And so again, these things are happening at such enormous energies, and it's happening so quick that you need things that, you know, can register them as successively as they go out, and to eventually stop them, you know. So you need to, ideally want to find the thing that actually stops it too, and really determines its final energy. So that's what these are for. I mean, that's why you need them. And you know, it's a camera in the sense of more of an electronic camera now, where you have things, you know, like in a camera, the photons are coming in, and you know, can activate various pixels or something like that in a digital camera. And that, in a sense, is what's happening here. These charged particles come through, and you have various wires. You have various electronics there that pick up these charges and send information about where exactly it happened. And you know, you reconstruct. You see, oh, this thing looks like this particle has gone in this curve in this direction. This one looks like it's curved off in this direction, and this one stopped here, and this one suddenly looks like it branched out, and other things came out of it. And you know, using our current theories, we can reconstruct what those are and predict where things should go and what should happen. And so that's what you know, that's the sort of the origin of these things, and why they're so big. But as Monica says, it's not like it's just a lot of rebar and space. It's like, you know, a 7-story Swiss watch. Everything,
Right.
this is, you know, this is custom built. I mean, this is all things that, you know, there's no place that's really using things at this level. I mean, you know, one of the things is that in getting to this level, they've had to develop technologies that are used in many other fields at a lower level, right? I mean, so it's taught us a lot about imaging and cryogenics, superconductivity. I mean, magnets, and it generates so much data that it has also necessitated a better understanding of how can we process so much data and information. And so, you know, famously, the web language was invented at CERN by Tim Berners-Lee in order initially to just be able to communicate with all the physicists to distribute all the information.
The World Wide Web, right?
The World Wide Web, right? Yes, exactly. So right. So that language, that protocol was developed there, and thankfully, because it was not, they don't charge for it. So, you know, it was made available. I mean, CERN, which is the overall research facility where the LHC is not a profit. It's a nonprofit organization. It's for the, you know, universal pursuit of science, and so it was sort of made available to everybody. You know, if it was a private enterprise, every time you did a search, you'd be paying somebody.
Yeah, it's amazing, all the different people from different countries, even countries that are enemies of each other, all these scientists working together on one massive thing. And I mean, I think that's the biggest man-made machine on Earth, right? So if I understand correctly, there's basically a fork in the road. There's two different general possibilities for our understanding of the universe. There's either the multiverse, which means everything's chaos and we can't understand. We're never going to be able to understand everything because we're only like a compartmentalized universe on our own, and we'll never be able to get any other particles. And then the other fork in the road is called supersymmetry, right?
Yeah.
Can you explain that a little bit better?
Yeah. I mean, I think these are two alternatives that are, I mean, in terms of how we view the universe, we know that our standard model, the theory that we have right now at the most fundamental level of how does the universe work, is called the standard model of particle physics. And it's based on the idea that there's a certain, you know, number of the most elementary particles and certain forces that they interact with, okay? And so there's a finite number of particles, we think. Basically, there's things called quarks, and there's things called leptons. And so the quarks are quarks, and the leptons are things like electrons and muons. And the idea is that these are fundamental. There's nothing smaller. They're not made up of other things. And there are certain fundamental ways that they can interact. They can interact with by magnetic means, which is the way we mostly are familiar with, which is, when particles have charge, that they can form electric currents, they can form magnets. We know that is both electricity and magnetism now are sort of combined, or one force, really. There's something called, gravity, we know, is another fundamental force, that anything that has mass, there's an attraction to it between them. We know that there's something called the weak interaction, which is something that is responsible for the fact that some particles decay, and you have radioactivity. So the reason we have radioactivity is particles, there is a certain instability, they decay into other things. So a neutron, for instance, can decay into a proton, an electron, and a neutrino. And then we know that there's something called a strong force, which is understood as a necessity because we know protons are not fundamental particles. Protons are made up of quarks. And so there's something that's holding these quarks together that is very strong, because quarks, they have charge, and they would not stay together necessarily, and they have to be kept very close together. So there's something that's a very, very strong force as well. So we have those four forces: a strong force, the weak force, the radiation force, the electromagnetic force, and gravity. And this has been incredibly successful as a theory. I mean, it explains pretty much every phenomena that we see on Earth. In terms of its accuracy, it's the most accurate theory of science in terms of the scale that it can get down to and the scale that it can get up to. But we know that it's not the end story. We know that there are things it doesn't explain. As soon as you look up into the sky, into the cosmos, there are very big questions we don't understand. We know that there has to be more mass out there than can be accounted for by the particles that we see. We can see that things, essentially galaxies rotating and things like that, we can tell there's something that is gravitationally pulling it, but we don't see it. It's not visible, and so it was given the name dark matter because it's dark. We don't see it. We also see that the universe is expanding. It's not only expanding, it's expanding at a faster and faster rate. It's accelerating. It's going away from, it's expanding at a faster and faster rate. So there's something, we understand that as meaning something in a sense is pushing it. It's almost like it's pushing it out. And we don't understand what that is. And that's we call that dark energy. We also...
How can we tell that it's expanding faster?
Well, you can tell by when things move away, light, there's something called a Doppler shift. There's a red shift. So it's the phenomena when, for instance, you hear a siren, and a siren approaches, and you hear it as it approaches, the frequency goes up and then comes down. And that is a shift in frequency, and that happens with light as well. And so stars and various other things, they emit light with certain colors. Okay, I mean, light, different frequencies of light correspond to different colors, and any source of light has a very distinctive pattern of the colors that are in it, essentially. And when things are moving away or moving forward, that pattern shifts. And so we can tell by examining the shift how fast something is moving towards you or away from you. And so by doing these detailed spectrographic analyses, they can tell, the speed at which something is moving. And they can tell the things that are further away are moving faster than the things that are closer. Again, looking at examining the time and studying the movements of these things, and studying this redshift, this shift, they can get an idea of how fast these things are moving away and how far they are as well. And so, it's incredibly detailed astronomical observations that have really allowed these things. So, we really, yes, it is. How do you tell what's happening that far out? And it's from very detailed spectrographic analysis, really, of the light coming from the light. I'm saying light, it's really electromagnetic radiation, in all its forms. So that includes, X-rays and infrared and visible light and ultraviolet and everything like that. So they look at, they have things that are sensitive to all these different frequencies. So we know that there are these fundamental problems, and there were also fundamental questions about, well, why is the universe the way it is? Why there's a different range in strength of the forces. Okay, gravity is very weak compared to electromagnetic forces, for instance, and you can see that just by the fact that I can just lift up, an object like my glasses, and the forces that I'm using to lift it are basically it's electromagnetic forces. It's that's what allows the arm. It's biological. Movement is contractions of muscles, which are ions moving in the arm. So it's electromagnetic. It's fundamentally electromagnetic. But just little me with my arm lifting this can overcome the entire gravitational attraction of the Earth. So that just gives you an idea of how much weaker gravity is than electromagnetic forces. And similarly, there's a real hierarchy in the strength of the weak and the strong force. And so this is another thing that really was very, very difficult to understand. And there's things in the theory that really don't predict this at all. And there's, in terms of the acceleration of the universe as well, we don't understand this. And if you try to do a calculation based on our best understanding, it's humongously off. The calculation is humongously off. It's really one of the worst predictions in science. And so again, this is a question of, well, what are we missing? And what's really interesting is it seems to have a very specific and sensitive value. This value at which the universe is accelerating, what this force is that's pushing it out. Because if it was a little bit more, if the force was, if the force was a little bit more, or the gravitational force was a little bit less, then things would never have actually formed. We never would have, after the initial Big Bang, they never would have come back together again. Gravity would not have been strong enough to pull it back together. But if it was too much, then if it was too much, then things would not have expanded at all, or it would not be accelerating. So there seems to be this, what we don't understand, that there seems to be a sensitivity and sort of a very specific number that accounts for this balance between a universe that would never form and a universe because it just flew apart, and it would never form because it would just never expand. So there are these various issues, and traditionally in physics, we've tried to understand things in terms of the fewest number of particles and certain, there's certain patterns and symmetry. And that has been the approach that has worked up to now. We've seen certain parallels in particles, that they have counterparts to things. And, it's sort of like a right hand has a left hand, and a positive charge has a negative charge, and a spin up has a spin down, and various things like this that have a certain symmetry. And so the hope has been to try to understand any new particles that might be necessary to understand these odd phenomena in terms of the things that we have, that they're related somehow, that they sort of fall into the same theory, and that we just haven't seen them, but there's something that they're going to fall into the same pattern. And again, I'm behind me have this illustration of the standard model of particle physics. It has this very nice symmetrical, round structure. And the hope was that maybe this could be expanded in terms of other symmetries, other parallel things, that would follow the same pattern. And these theories, are called supersymmetry. The idea that there's additional symmetries that we are beyond what we know now, but we could mathematically see that they could work. And mathematically they're allowed, and maybe there's particles that would correspond to that. And so that has been one of the big hopes at the LHC, is that we'd see new particles that would fall into these new patterns, and that could be part of our theory, our expanded theory. But we haven't seen them. And so this alternative idea has arisen, is that maybe we're asking the wrong question in a sense, and we shouldn't be asking why do these numbers have very specific values. The number that determines the expansion of the universe is something that's called the cosmological constant, and maybe we shouldn't be asking for a theory that's going to predict that number, because maybe it's not a special number in general. It's a number that happens to be special in our universe. And so the parallel that's often made is, if you look at the distance the Earth is to the sun, and or any of the planets to the sun, and you could say, well, why is it that distance? I mean, with the Earth in particular, you say, why we have this very particular distance that's just right, that it's not too close where it would be too hot to allow life, and it's not too far where it would be too cold to allow life as we know it. But what we know is that it's not, there's not a theory that says the Earth has to be here. In the aftermath of the Big Bang, I mean, things fell into various distances just because of the way things were exploding and gravity, and they fell into them. And this one at this distance is the one that allowed life to arise.
It just got lucky.
It just got lucky. But, Mars was not so lucky. Saturn was not so lucky. As far as we know, any of these other ones are not as lucky. And so this has been this wild idea that maybe there are other universes, and ours is the lucky one that has this expansion that allowed a universe to form. But there could be other universes where things are not expanding the way they are, where they didn't, or where, maybe it's another universe. It's, of course, it's hard to even say, well, what's another universe even look like? But, say another universe that also had a Big Bang or something, and that the acceleration is different than ours, or that, it never expanded the way we're expanding. And so this idea, which is a theory called about that there are multiverses, is a competing scheme, and it's a very different way of looking at the problem, and it's controversial within the physics community, because in some sense, physics has always worked on the precept that we could find a an ultimate theory that would explain everything.
Mm.
But this is an alternative that's gained more ground in the last, 15, 20 years, especially the last 10 or 15 years, which is basically saying, it's the wrong question to say, how do we predict that number? So it'd be, you'll never predict the number because it's a matter of chance that it came out in this universe that way. There's some support for this idea from other theories. There are theories like string theory that seem to indicate the possibility and maybe necessity of different universe configurations.
String theory?
String theory, yes. Okay. So a string theory is a theory that basically one of the biggest outstanding problems of physics is that the weak, the electromagnetic, the strong interactions are all, in some sense, fundamentally built the same way. They're quantum field theories. They're quantum, really. And gravity is not. Gravity, our best theory of gravity is Einstein's theory of called general relativity, which is a theory of gravity, and it's really just a complete outlier in terms of how it's set up. That Einstein gave a theory that basically said gravity is because of curvature in our space and time. That it's a very hard thing to picture, but we come up with three-dimensional images of surfaces that are curving, and mathematically, Einstein showed that if you think of 4 dimensions of the 3 dimensions of space and time, we can study those things geometrically, mathematically, and the mathematics shows that if you think about curves in space-time, that is completely equivalent to the force of gravity. Because gravity, we know gravity affects anything with mass. And so anything in the universe that has mass, is occupying some space and time. And we can say that if you move, if you bend space and time, things are going to move in a certain way that's gravity. But this is a very, it's completely separate from quantum mechanics. And so, the holy grail of physics in many ways has been to figure out a way to unify quantum mechanics and gravity. And one of the candidates that has been, being worked on now for also quite a number of years is something called string theory, which, in a very simple manner imagines that the little fundamental particles are not like little points, balls, but they're little vibrating strings, and that it's the different frequency vibrations that might correspond to different types of particles, and interactions are the interactions of these things. And there's hope that this might be a way to unify gravity and quantum mechanics. And there are also indications in string theory that you may need other dimensions, and it gives some credence to the idea of a multiverse. Again, I mean, these are none of this is completely proved, but there are there are overlaps that support it. So I think that has given more weight to the arguments of a multiverse, in the later years, in the last years. But it's still unclear, which way it's going to be. And so experiments like the Large Hadron Collider, I mean, the big thing with the Large Hadron Collider is that in the standard model of physics, there was, even though the theory worked incredibly well, at the center of it was this thing called the Higgs boson, which was necessary for the theory to work, but had not been seen. And in a sense, the LHC was designed to, really determine yes or no if the Higgs existed, and it did. And so in some sense, it was this incredible success. I mean, it was just the ultimate confirmation of, a theory, when you think about it, just this incredibly abstract theory that is incredibly elaborate and accurate and, ultimately explains all of the everyday phenomena we see on Earth. And they found it, with this enormous machine that is mind-boggling, and, the evidence really was convincing that yes, there is this Higgs particle. But so that sort of capped off this nice picture. But then, of course, it's like you look outside and there's everything else that's going on, and it didn't. So I think what physicists, they, in some sense, you wanted to find a Higgs, but the real hope is they find something else to sort of start to indicate what is the bigger theory.
What exactly is the purpose of the Higgs, and what other particles have they found since they discovered the Higgs?
Well, the Higgs is it's a very unique particle. It's the only one of its kind that has certain properties of what are called spin and its mass, and it's in a simple way. We understand that it's necessary for particles having mass, for them actually having mass, that the theory itself in quantum field theory is a great theory for particles that are without any mass, the way they interact. But in order to essentially explain certain mathematical aspects of it, you need something like a Higgs particle. You need a particle that has the properties of a Higgs mathematically to have the theory work out, and have masses and things like that. There's a lot of analogies people make, and some of them are better than others, but the one that's most often used is the idea that the Higgs is this field. It's a field that permeates everything, and particles moving through the field get mass. I mean, and the simple analogy being, throwing a ball through the air versus throwing it, trying to push it through water or molasses. That the different the medium that things move through determine its mass.
So the Higgs is like the medium.
The Higgs is a medium. So the Higgs is, fundamentally the Higgs is something we call a field. And, what we believe is that in the very, very early universe, right after, the Big Bang, in some sense, this field turned on, that suddenly this field turned on, or it was created at this early stage. And particles attained mass and, began to have the interactions that we know. So the Higgs is a field. What we know is that in a field, when you combine these particles, you can excite the field, and it manifests itself as a particle coming off. And so that's what the Higgs boson is. The Higgs, when they see the Higgs particle, it's a perturbation in the Higgs field, that when we combine these things at such incredibly high energies, and it creates a disturbance in the Higgs field that we see as the Higgs particle, as the Higgs boson.
So is there any way, or are there any theories that suggest that there could be like dimensions that we can't even perceive with our senses?
Oh yeah. I mean, we can't perceive with our senses more than,
right.
4. I mean, the 3 the 3 space dimensions and 1 time dimension. So yes. So that is the question. I mean, all these ideas, many of these ideas, well, certainly string theory posits more dimensions. This question of multiverses is, do multiverses correspond to more dimensions? And, there's various theories about, why don't we see them? Is it possible that there are these dimensions, but somehow they're they're all crunched up. So beyond our dimensions, they're crunched up and they're so tiny that we can't see them. They're folded on into each other. But yes, I mean, we don't see these dimensions clearly in our normal activity. But there are theories about how, if they exist, they might be manifested. Okay, and I mean, again, just to give you an example of what this could mean, it would mean essentially it would be a bizarre phenomena where something might just appear. So one of the classical examples is if you think of the fact that, suppose you lived on a piece of paper. Suppose we lived in 2 dimensions. Mm-hmm. So a piece of paper is just 2 dimensions. And you walk around, you're just on the paper. You can't see above or you can't see below. So all you can see is what's in the paper, in the plane of the paper. And now suppose there is another dimension. You're not aware of it, but there is another dimension, and some ball, comes in and enters your universe. Well, what would you see? You would see, when it first touches, you'd suddenly see it's a spot. And then if it's a sphere, you'd see it expand. And as it goes through, and passes through, the spot would get bigger and bigger, and then it would get smaller and smaller, and then it would disappear.
Right.
And so it would be this phenomena that you would not be able to explain with your normal theories of, you've never seen anything like this. Suddenly something appeared mm-hmm. and disappeared. And that would be evidence of something, possible evidence of something from another dimension. So, that's in a sort of a one simple way to imagine what does this mean? What would it be if there's another dimension, and how could we detect it? And so we look for strange phenomena like that that doesn't fit into our theory, but might fit into how it would work if it was, if it was coming from another dimension.
Right. It's not something that you could explain with just shapes.
That's right. You couldn't, or, just like, forces that we know and things like that. So, right. So, evidence, of other dimensions would be really weird phenomena,
Is there any weird phenomena that sticks out that people that we've found in the past decade or so that hints to anything like this?
Not that I know of. No. Okay. I mean, no, like sudden appearances of a UFO or things like that. Yeah. So, no, I mean, that's what they're looking for, is they're looking for things that don't follow the normal rules of physics, but might follow, but might be explainable in terms of some of these other theories. And there are other theories that do explain these, and using other ideas and multi-dimensions and things, they can try to explain some of the missing understanding in cosmology. But that, there's nothing that's definitive for sure at this point.
Have you heard of this element called 115? I think it's 115, I believe. A new element that was recently discovered in the past, I believe, in less than 10 years, where I think I've heard Bob Lazar talk about it, the guy who was working in Roswell at Area 50 or near Area 51. And I believe it was an element that was used to basically fold gravity. And it was basically the story of him is he worked at a secret base near Area 51 where they found these outerworldly crafts that the way they moved was, instead of using a combustion engine to pull air in and shoot air out the back, what it did was it bended gravity around it to accelerate in any direction. Like there was no acceleration. You don't start off slow, get faster, and then slow down. It's just instant, up, down, left to right. And apparently from what he was explaining was that it's this special element called 115 that enables these crafts to basically fold through gravity and use gravity to propel itself in any direction.
I don't know anything about this, I have to say. Yeah.
Yeah, it's fascinating. So yeah, what particles have been found besides the boson, the Higgs boson,
Well,
since your documentary?
well, there's have been no new particles. I mean, there's no, there's no fundamental new particles. I mean, there's certain variations of things, certain things that have certain properties that we didn't expect. But in terms of anything beyond the standard model, which is the quarks that we know, the electrons, the muons, the neutrinos, they have not found a new particle that doesn't fit into this paradigm. So, that begs the question: is the theory wrong, or is it just that we don't have enough energy? Because the problem is these theories, they don't really predict definitively what the masses of these particles are. We had a certain idea of what the mass of the Higgs should be, around what it should be, but it's always a question: are we at the high? Are we at? Because we know that you need higher energies to find these particles. I mean that that's one of the reasons we don't see them, is that they don't exist normally. They're not stable. I mean, even the Higgs boson, it doesn't last. We don't really even see the Higgs. The Higgs almost immediately decays into other things. But our theory predicts what it should do, and that's what they find. The idea still is that for many people, they think that we need even more powerful accelerators. We need to get to higher energies. But of course, the question is, well, how high? And it's very expensive and technologically difficult. But there are efforts now to build a successor to the LHC.
Really?
Yeah. I mean, there's
What would
plans.
something like that look like?
Well, again, you could do it could either be a big ring, another ring, even bigger, or the other alternative is a linear collider, where you have things that are originated at two ends, and you just accelerate them right to each other and bang them together. And so there are proposals in Asia, and there's a proposal at CERN, but these are 20, 30-year plans. So the LHC itself is still very active. They actually have just upgraded. They're in the middle of a big upgrade. So they already have they're going to have the capability to go to higher energies, and they keep improving their optics in a sense. So they've upgraded both the ring to get higher energies and more accuracy and more what's called luminosity. So these are bunches of things that come together, and the more you can focus them, the more collisions you're going to get. It's not, and that's not just one proton. These are packets, of millions and billions of protons, and they sort of fly through each other, and you get a certain number of collisions. And so, of course, if you can focus it more, you'll get more collisions. So they're improving that. They're improving their detectors, their ability to detect things. And then they're also starting to lay the groundwork for what could be the next generation of things. As well as, there's also a lot of efforts to see, can we learn anything about this from alternative experiments? And there are alternative experiments that are looking at other phenomena, that are looking at the way these things called neutrinos behave. Neutrinos are, these light particles, very, very light particles that are, involved in weak interactions, and they pass through almost everything. But they have very unusual properties, and they might be able to shed light on some fundamental problems. And so people are looking for them, often in deep caverns in the earth, where they build them really, really deep, and in mines and things, hoping that they can stop them and analyze them. And then, more and more astronomical studies where, people are hoping, as our sensitivities are getting better and better, and they're coming up with new techniques, maybe they'll find something that sheds light on issues like dark matter and dark energy. So You know, the problem is, I mean, the scale of these things now are huge. And so, of course, they're very expensive. And this gets back to, you know, the issue we talked about right at the beginning of this is what is the value, you know, what value does society place on these things that are, as Sama said, not necessary for survival, but they are, you know, intrinsic to our need to understand and our curiosity. And, you know, that's something we as a society have to evaluate.
Well, that's an interesting question. How much money, do you know how much money has been dumped into the Large Hadron Collider to date, or into CERN, and who pays for all that?
So, I mean, I think the construction of the Large Hadron Collider was, I think they say about $10 billion to, you know, to get it to the point of finding the Higgs boson. It's a consortium. So CERN, which is the consortium of countries, was actually an outgrowth of UNESCO. So it was created shortly after the end of World War II. And it was a consortium of European countries that the idea was to unite these countries who had been very recently enemies into the peaceful pursuit of science. The idea is that science could be this unifying endeavor. That, you know, there's a truth to science that would transcend political differences and opinions and things like that. And so there are these founding, you know, members of CERN, and they each contribute money based on their size. And so that's where a lot of the money comes from. And then there are other affiliate countries and institutions that contribute money for the privilege to be able to work on these experiments. Because, you know, essentially, if you want to be at the forefront of understanding particle physics, you need to be, you know, participating at CERN. And so other countries like the US is a huge contributor.
Are they really?
Yeah.
I was gonna ask you, how much of this money does the U.S. How much input does the U.S. have, like, financially, into these studies?
You know, I'm not sure how much, but I mean, it's probably at least, I don't know. I mean, again, I'm not sure. I'd say order of magnitude of 200 million or something like that. So it's not inconsiderable. And so what happens is it can come from the US government, but often also from universities. So universities that want to participate, they want to send their students there, then they contribute and they get affiliated with one of the experiments. So whether it's ATLAS or CMS or LACB, they contribute a certain amount of money, you know, for their students to go and to work there. So that's what you saw in the film, is that Monica, the graduate student Monica, she was formerly, I think at that point, she changed. She was at University of Pennsylvania, then she was at University of Chicago. She was formerly a University of Chicago student. She was living at CERN, working at CERN full time. But, you know, it was the University of Chicago collaboration that was working on ATLAS. They, you know, contribute a certain amount of money to do that. And they build things, they work on it. So they work on the detectors. So CERN itself is really, I think, I believe, really supported by the members. You know, so that's the ring. You know, that's permanent staff. You know, I think there's 1,500 or so people that are permanent there that are part of CERN. The experiments are really, they're independent things. They are, and they're supported by the institutions that participate in it. So all the universities that work on ATLAS or ALICE or LACB or CMS, they are independent organizations, groups of universities that come together. Yeah, we want to work on this together, and we're going to put this much money into the experiments. So the funding for the experiments is a little different from the funding of the ring, that they maintain the ring.
The interesting thing to me about all of this, I think the most interesting thing to me is that, there's so much that goes into this massive, massive undertaking of the LHC and all the experiments that go on. And it's a very difficult thing for a normal everyday civilian to wrap their mind around, right?
Hmm.
Um, Normally if someone explains this to somebody who's never heard about it, you say, well, what's the point? What's the goal? What's the goal of all this?
Hmm.
But what I've realized is that no matter what the goal is, the coolest thing is that all the things that you can discover on the way to that goal, like, for example, the World Wide Web,
Hmm.
like all the different innovations that come along in the process of trying to reach some peak, you know what I
Hmm.
mean? Or some summit of some big discovery, some aha discovery,
Hmm.
is that the interesting things that are innovated or discovered or learned about on the, during the process.
Yeah, well, I think that is exactly the point, and again, it relates to this question that we brought up right at the head that Savas encapsulates in other people is that, um, the people that do this for the most part don't do it because they want to um, make a better mousetrap. They're doing it because we want to understand, but the offshoot of that is unpredictable and immeasurable, and it has resulted in so many other things. As I say already, I mean, from the LHC, I mean, the advances that we've gotten in understanding, how to work with super cool temperature things, materials sciences, optics things, magnetic phenomena, information processing, the web. Um, yeah, I mean, even just at the simplest level of information. I remember a number of years ago. We obviously are having an information explode. We're living in an age of information explosion, and a cousin of mine was working in the field of bioinformation, and in particular dealing with all the sequencing and our understanding of genes. And this used to be very hard and expensive, but it was changing where now the cost of sequencing DNA was getting less and less and easier, and suddenly people in biology were being faced with an enormous amount of data, and they didn't know how do you deal with this, and so they decided they need to seek out the advice of the people that deal with the most data of all, and it's the people at CERN. And so they went to them and talked to them. And so one of the things that was interesting, he had said at that time, is that at CERN, the amount of data created at the LHC, the trillions and trillions of collisions every second, it's impossible for us to imagine. We can't deal with it. Okay, it's happening too quick for our computers. We can't possibly store it all. And so the first stage after the collision is that it goes through an analysis. It's called the trigger, and it immediately throws away a huge amount of data, which is things that they already know about and are not interesting. And so it filters out at the very first stage a lot of uninteresting things that were not needed. There's a lot of junk, a lot of things that aren't interesting.
Wow.
And because they just can't even deal with anything else. So this is a very, and of course it's a very tricky thing because you're throwing away data. But there's no alternative. We just couldn't deal with it. And what my cousin had said is at that point, he said biology wasn't at that point where they could imagine throwing away data, but they were going to have to get to that point, because there was, and so how to do that intelligently is something, again, it's not something you would even expect necessarily would be a result of the, physics, but it's part of it. And it's one of the things that has been an outgrowth of this, you're pushing the frontiers of understanding in science and technology, and that does eventually have, it can have a certain unexpected benefit. But
So you're saying these when they collide all these particles, when they use this thing to collide the particles and these atoms together, whenever there are events that we've seen before during those collisions, we're able to just filter those out and only take the new things that we've never seen.
Right. Yeah. Yeah. I mean, not so simply new and old, but yes, basically, exactly. That there are a lot of things that are happening that we know are not interesting. You know, there are a dime a dozen, and just seem, relics of something, and just see just focus on the new ones. Yes, because we can't possibly keep all the information. They can't possibly keep it. So, talking to people that are on the trigger division at the various experiments, they become very very popular with their collaborators because certain theories predict certain things could happen. And so it's a very tricky, you have to make some, tricky decisions about, what things you're going to eliminate, because everybody may not agree on what are the interesting things, but they have to make certain decisions, or they couldn't possibly deal with any of it. So
how are those just sort of like clickbaity headlines where they talk about making little black holes with the LHC, or like purposely creating black holes?
Well, mostly, yes, you're seeing clickbaity things. I mean,
Yeah.
so the theory does predict that it's possible that it could create really mini black holes. But the idea that it would create a black hole that would destroy the universe is just complete fiction. And, it was, astonishingly, it was mostly promoted by this, ridiculous high school science teacher in Hawaii. And, but because it had such, sensationalistic aspects, it was picked up by the press everywhere. And this guy really knew nothing. I mean, in fact, as they said, if he read the next lines in a paper, in any of the technical papers, the same theory that predicted that you could possibly create a mini black hole also predicted it would evaporate almost immediately. So, but unfortunately, it did get the attention of the press. And I remember I was over there at CERN right before the first big turn on, and there were big headlines, and so it did force the administration to basically take a couple of physicists and say, okay, you really need to do another study, just definitively show that this is not a problem, which they did. But the other argument is that in the cosmos, there are collisions happening at far, far greater energies than we can ever create here. And the universe is here. So, if this was really a problem, if these high energy collisions could create these things that would destroy our universe, they most likely would have already happened, and we wouldn't be here to worry about it.
How are we ever going to figure out what dark matter is?
I
mean, it's basically just blackness, nothingness, right? That's how we can perceive it.
Yes. Well, but it does have effects on mass and things like that. So, we do, dark means that it's not visible electromagnetically. It doesn't mean that it's not that it doesn't interact in other ways. We know it interacts gravitationally. So we can detect things that don't emit light because of the other properties. I mean, there are other particles that, don't emit light, that don't have a charge or something like that. So we can detect them because of their interactions through these other forces. Okay, does that make sense? So yes. You're saying, how do we detect something because we can't see it? But seeing is only one way of detecting things. We can detect things, which is how we know that it exists, which is how we know that dark matter exists, because of gravity. So it affects other things, right? So if you saw something rotating, so you saw something that you can see, and it's going around in a circle. To keep something going in a circle, we know is gravity needs to keep something going in a circle. There needs to be a force. Okay, I mean, even at the simplest level of Newton's laws, we know that things, if they don't go in a straight line, there's got to be a force that's holding it in. So the reason things, any object with mass moves around something is because something is holding it in. Now, that something could be electricity and magnetism. And so if you have a positive, or say you have a positive thing at the center and an electron around it, like, this primitive idea of an atom, right? An electron. Okay, it's the electromagnetic force that's holding it together, right? The attraction between positive and negative charges. You have the Earth going around the sun. It's because the sun has a huge mass, and the Earth is also has mass, and it moves around it. But suppose it's possible that you don't see something. So suppose there's something out there and it doesn't emit light like the sun, but we see an object, we see a planet moving around something. Okay, or even what we see is sometimes whole galaxies moving around something. We know something is there. Something is there. We can't see it because it's not emitting light like the sun, but we know something is there. And so that's how, if you study the motion of these things, what the speed is, what the distance is, what the curvature is. Again, the curvature is really important. How we can tell what the strength of this thing is, and we can tell properties about it, even though we can't see it conventionally with light.
Have you ever seen the movie Interstellar?
Yes.
What did you think about? What did you think about it? Did you like it?
Personally, I liked the human story the most, but I think
I've heard
Kip
that
Thorne was involved in it. I mean, in fact, I think what I read is actually one of the originators of it, and so Kip is a very, very respected physicist, and they, I think, made it as realistic as as possible, and in a speculative way. So it was very, very legitimately done. I know that the graphics people actually really worked with scientists, and even I think may have even written a couple of scientific papers on how do you visualize certain of those aspects of it and things like that. So it really dealt with that as well. Again, it is, for me, an interesting thing is I primarily I consider myself a filmmaker at this point. And so when I look at a film, I'm looking at how they are dealing with that aspect of it. And I thought there were some very interesting things there. I thought, with the, I actually thought the way that they handled some of the things nearer the end with the different dimensions with the daughter and the father was very, very interesting, actually.
The hardest part for me to conceptualize was the way that time changed.
Mm-hmm.
How he got farther away from the Earth and time went slower for him than it went on Earth, because when he came back at the end, his daughter was like 100 years old and he was still like the same age.
Right. Yeah, and that's a function of relativity. It's part of Einstein's theory, and in terms of how the time and space dimensions get altered, and again, in a similar way to, somewhat parallel to what I was talking about, the way things shift when they're moving in color, right? That you shift frequencies. There's a certain sense to it. You can imagine that it's time also can be changing. That when you're moving, when you're under the effect of a field, of a strong gravitational field or something like that. So I don't know if that helps at all, but think in terms of the way we know that sound or colors can shift when you're moving. Well, time as can as well, actually.
I think the next thing that we're going to discover at CERN is time machines. I think that would be pretty cool.
That would be cool.
What else are you working on now? It's been a while since you released that movie.
Right.
Was that 2014 you released that?
Yeah, it premiered at festivals in 2013, and we sort of did the festival run for 2013, and then it actually came out in theaters in 2014. Um, and so it was nice. I mean, I think that we had the benefit of a discovery that was on the front page of essentially every newspaper in the world, and people were interested in it. I mean, they are, people. We were surprised. I mean, look, when I started, I had no idea if anybody would be interested in this sort of film, and it turns out that there's a lot of people that are interested in these questions and these fundamental pursuits. Yeah, that went through 2014, and then I actually got involved in. I made a new film about a man named Claude Shannon, and Claude Shannon is this unbelievably unknown genius who essentially laid the foundation for the information age. And he is somebody he really is the person that first realized what the significance of bits, and that everything could be converted to zeros and ones. I mean, he was looking for a universal theory of communication. So this was in the 40s, late 30s, 40s, and we had all these different things like, we were developing radio and TV and text and all sorts of things that you wanted to communicate. And what Shannon realized is fundamentally, what is it? It's about communicating information. You're transmitting information. And nobody had really, there was no real theory of information. I mean, I think information was considered to be this sort of abstract thing. Probably people thought, well, information is about data and amount of information. How would you measure information? Well, it's like the amount of text on a page or something like that. And what Shannon realizes that information is fundamentally, it's about the resolution of uncertainty. So it's something you didn't know, and now you know. That's the basic unit of information, is you find out something that you didn't know, and now you know. And that he realized that it basically could all be reduced to this simple binary thing of, not know or no, or true or false, yes, no, 0 or 1, a bit. And so he realized that, you could, if you changed all information, if you reduced it, if you changed it all into, basically this question of a 0 or a 1, you could have a universal theory. I mean, this would apply to any information, whether it's, text or pictures or sound or things like that. It's all the same then. It's all zeros or ones. And you could come up with a mathematical theory. And he showed how you could measure it. You could measure information mathematically, and then you could optimize it. You could talk about compressing it, because he realized that a lot of things are redundant. And so he looked, initially at that, like the English language, where we know that, if the whole notion that, I mean, if you have a Q, the U is going to generally follow. And there's a lot of other things that we have incorporated in our grammar and patterns. And he, looked at it in a more general sense, realized that, there's a lot of redundancy you don't need, so you could compress information, and that you could transmit it, and that you could actually come up with a theory of how to overcome errors in transmission of information. And that, if you had a good theory and an understanding of what you have, you could essentially code it in certain ways that could compensate for errors. And, the earliest, most popular manifestation of this was, when we suddenly had CDs that could compensate for scratches, because, they could overcome scratches, as opposed to an analog LP record. But, digital media could often be encoded in a way that it could compensate for scratches and things like that. And so it was this, comprehensive theory of communication that allowed you essentially to, if you were clever enough, to code things in a way that you could have efficient and perfect communication. And
it seems like such a distant memory of playing a CD in a CD player and having it skip. Remember when you'd bounce
yeah,
it or you'd vibrate it too much, the music would skip.
yeah.
What was this guy's name again?
Claude Shannon.
Claude
Yeah.
Shannon. What led you to discover this guy?
Well, it was actually a friend who is an information theorist who told me about it. He was a friend, and he said he has an idea for me for another film. And he said it's about Claude Shannon, and I admit I didn't know who Claude Shannon was myself, and then started reading about it. And you start thinking, how could we not know about this person? He, is so fundamental to everything in our modern world. And in a sense, he did three major things as a grad student, for his master's degree. He actually was the first person in 1938 to realize that you could meld something called Boolean algebra. So Boolean algebra was a mathematics of thought. I mean, it's basically, you see these sort of logical arguments that, so-and-so does this, so-and-so does this, then this does this. And, it's sort of the logical statements that can lead to a conclusion, that children don't like alligators, alligators eat children. You could do this sort of series of things. And they were all just, it was basically logical statements. And he showed how you could make those mathematical. And they were all just being about true or false. That statements were either true or false, and you could make logical arguments. And, it was the basis of, how we think that this is a logical argument. And what Shannon realized is that basic, true-false aspect could be mapped to electric circuits, which are either on or off. And so the on, a circuit is either on or off, and then that could correspond to true or false. And he showed that basically any logical argument, you could have an electric circuit to mimic it. So you could basically make circuits that could do logic. And so in a sense, it's the basis of the idea of a modern computer that does something more than just, adds numbers or things like, or makes steam.
Like
so,
something that's true or false?
Yeah, so true or false could correspond to just, whether a circuit is on or off, whether a switch is connected or not. And so, the basis of this idea of a computer that, really could do logical operations, it comes from this. And this was his master's thesis. Then during the war, he was working, he was at Bell Labs, and he was working on cryptography. And he wasn't that interested in, specifics of code breaking. So, a lot of the effort during the war was, how do we break a code? This was like the Enigma with Alan Turing and things like that. But Shannon was really interested in a much more theoretical, fundamental question is like, what is a code? And how much information do you need to break a code? Can you make a code that's completely unbreakable? And so he wrote a paper that basically people consider as the foundation of theoretical cryptography. And then he really he came up with this theory of information theory. And it was really, he was working on it on and off for 10 years and didn't really talk to anybody about it. It was just something, nobody else even was thinking that there was a theory of information, mathematical theory of communication like this. And he sort of wrote a paper in 1948, 2 big papers that just sort of created this field and threw down a challenge basically, because he predicted that if you could find the right way to code things into zeros and ones, if you could find the right way to code things in zeros and ones, and then to compensate for errors, that you could have perfect communication. And he, threw this down in his paper in 48, and it took until the 90s to basically be able to prove everything. And people began to use it right away. And it was very important for even for like the Voyager, for our satellites. The reason we can actually communicate over these huge distances, because they were applying principles that Shannon had laid down in terms of how you could compress the signals, how you could compensate for the noise of millions of miles of travel. And it was used in, obviously compression is something that is critical to our way of life. I mean, the whole idea, the way we compress images, the idea, the ability to be able for us to talk on Zoom and see images, yet it all comes down to basic principles still of what Shannon laid down of how to encode information, how to transmit it. So, it seemed like a worthy subject, but even more is that when I began to read about him, I found out that he was a really unique individual in terms of he was a very playful. And there was a there was very little footage of him at all. And he was very shy. He didn't write a book. I think in terms of why don't we know about him compared to other people. But the IEEE, which is the Institute for Electronics and Electrical Engineers, a professional society, they did an interview with him in the 80s. And there were a couple of other interviews with him in the 80s too. It was at his house, and he was an inveterate inventor. He not only had the mathematical skills, but he loved to build things, and he had the ability to do that. And so he built all sorts of things. And so this interviewer came to interview him, and the interviewer wanted to talk about how he came up with certain theories and things, and he just wanted to show various things he had built, which included a juggling WC Fields and a flaming trumpet and a chess playing machine. And so he built all these things that just showed a sort of playfulness, that he had this curiosity of a child that he never lost. And sometimes it revolutionized the world, and sometimes it made a flaming trumpet. And so to me, this sort of, it's somewhat related to the bigger issues we've talked about of, pursuing pure science and the reasons for doing it. And Shannon epitomized for me somebody who just, he pursued things out of just curiosity, this childlike curiosity, and it had tremendous results. So he also, and I think that's another reason he's not so well known, is that after his paper in 48, he sort of threw this down as a challenge to people to try to prove it, to try to work out certain things. And he did some work on it as well, but then he sort of got interested in other things and didn't really pursue it as much. And so he got interested in chess. And so, in fact, Alan Turing came to visit when he was at Bell Labs, and they were both working on top secret things in dealing with cryptography. So they didn't talk about cryptography, but they both began to talk about chess and about the fact that, so again, this is in the 50s, early 50s, would a computer ever be able to play chess? And so Shannon actually wrote the first paper about how a computer could play chess, and built a primitive machine. It could only play 6 moves because the computers didn't have that much capability at the time. But he built the first, at least one of the first computers that could play chess, and wrote the first paper that I met some of the people at IBM that made Deep Blue. So Deep Blue was the computer that IBM made. That was the first computer to beat a world champion, a grand champion. So it famously won the grand championship of chess. And he said that basically everything still in terms of computer chess goes back to Shannon's paper, basically, that he laid the way for that. So he built that. He built, probably one of the first artificial development, artificial intelligence devices, of a little mouse that could find its way through a computer. He Then he got very interested in juggling and unicycles, and he came up with a mathematical theory of juggling. He built unicycles. So he just was sort of extraordinary, and he was very playful. So to me, again, I got interested in the idea of this film, first of all, I mean, to let people know what this man did, but also as a model of how. And so the film actually is I ended up doing a real hybrid film. And so where I was able to sort of recreate the interview. I mean, there was no footage, but I had this text and I sort of wrote a script based on that, as if we were doing it, and found somebody, had an actor, and we were able to film actually in Shannon's house, and we were able to get a lot of these devices. Some of the things he built were at MIT Museum and in various homes, and the family had them. And so we recreated the house, and used this interview, as the sort of core of the film, which was to really get the sense of Shannon as a person, and then have other people talk about him and illustrate some of the things he did. So that film, which is called The Bit Player, was something that I was working on, for a couple of years after that now, and premiered last year at the World Science Festival, and it's actually now out on Amazon Prime and on CuriosityStream. So that's, that was my last big effort.
What was the scientific theory for juggling? I'm curious.
Well, he looked at it from a mathematical perspective of as he said, how long the ball is in your hand, how long the ball is in the air, gravity, the size of the ball, as he said, even, how many hands, the speed at which you throw it. So, those are the different parameters that you can play with, is the theory of how high do you have to throw it, the speed, the number of balls. And so the idea of how could you come up with a theory of, was there a prediction for how many balls you could juggle, or what speed you would need with how many balls, and things like that. What height you should do it at, what speed you should do it at. Those are all the parameters that he was playing with. And then he built this mechanical W.C. Fields figure that actually juggled.
Really?
Yeah.
That's amazing how you can take things like juggling or chess and solve them with basic math equations.
Yeah, that's exactly it. I mean, that's the real genius, is how do you translate something like that into mathematics that can be useful. And that's what that's what Shannon did. Is he, in some sense, one of the genius things of information theory is that he was able to abstract from the complexities of the content of information, and so the content doesn't matter. That was, we're never going to come up with a theory of information that could account for all the meaning, because you can have, every book has different sentences, and you can't measure the meaning. But what you can measure is what you can measure is the uncertainty, the intrinsic, how much of something is new, how much makes a difference, and that you can measure, and it allows you to do so many things, like compress it, or compensate for errors. So it was this abstraction of information, separating meaning from an intrinsic thing that you could actually deal with. And it actually has so many consequences now in unexpected fields. I mean, when it first came out, there was a big move, people just were jumping on this idea of using it for everything, you know, gardening and this and that and landscape design and architecture and, you know, everybody, you know, in the social sciences, and we're all excited about this idea and using it. And Shannon sort of pulled back, and he had famously wrote in a short paper, you know, where he said people should get off the bandwagon, that this is, you know, this is a very specific theory and we're still working out the details, and, you know, we need to focus on that first. Mm-hmm. The irony is now it's continuing to have incredible amount of applications unexpectedly. And so, as you know, as varied as in genetics, where when we, you know, it's interestingly, I mean, relating to something I was talking about before, is, you know, when you try to sequence genes, we can't technically still, you can't basically do the whole thing in one strip. We can't technically get a whole strand of DNA. So what they do is they do it in segments. They have to break it up and do it in segments. And then the question is, how do you put these segments back together again so that, you know, in the right order? And it turns out that they're doing it using Shannon information theory. It becomes an integral point, an integral tool for how to see how these things go back together again. So he's actually having, you know, a role, and I mean, information theory is important there. It's turning out to be information in physics has turned out to be a very, very important concept. And for a long time, physicists didn't care about it at all. But it sort of changed with the idea when Stephen Hawking started talking about black holes, and black holes started becoming to be more seriously considered. And what you know, a black hole is something where basically, you know, everything, it's so strong, the gravitational force is so strong that everything that comes, you know, too close to it basically gets sucked in. Nothing can get out. Not even light can get out. That's why it's called black. Okay, so there's another example of something you can't really see, but we can see the effects of it. And we now know that there's black holes possibly at the center of every galaxy. Anyways, the paradox of the black hole were that it seems that anything you threw in would be lost in terms of the information. Hawking famously showed that, in fact, black holes can leak. That you know, because of quantum mechanics at the edge, things can leak out, but it's just a very diffuse radiation. So it doesn't reflect anything that went in there. So no matter what goes in there, you know, whether you throw an elephant in there or a book or anything like that, what comes out is all the same. And so information has been lost. We've lost the information about what went in there.
What do you mean what comes out is all the same?
Think of it as radiation. So, you know, okay, whatever, you know, more concretely, you know, if a certain star goes in, certain stars fall into a black hole, other planets, things fall into it. Yeah. What comes out is just a certain radiation. There's nothing that tells you what went into forming the black hole. Okay, does that make sense, or? Kind of
losing me.
Okay, so there's nothing, you know, it's just like, you know, different things can fall in, different planets, right. But what comes out is just light, you know, or heat. Okay, so it doesn't, there's nothing, we can't learn anything about what went into the black hole by what comes out. So there's information lost. The information about what the thing was that went in is not what comes out.
So do things, are you saying things actually are ejected out of black holes at a different position, like it's somewhere else?
No, not in somewhere else. That comes out, you know, it radiates. So we know black holes, we can see that there's radiation coming out, very, very low level radiation. Okay, which was initially thought not to be possible. It didn't seem like radiation is light. It didn't seem like anything could come out. We know things do come out, but what comes out isn't related to what went in. And it seems like the idea was it seemed like information was lost, that things fall into the black hole. It seemed like that we lose information. And now, and it's still a very hot topic, but it seems, and one of the things physicists have had to do is really go back to information theory and think about information carefully to try and understand it. And so it has, information theory has become very important in cosmology in terms of its understanding. So again, there are people that have claimed that information is actually more fundamental than a lot of, other concepts in physics. So famously, there's a physicist named John Wheeler, who basically Kip Thorne, I think, was Wheeler's student. And so Kip Thorne from, Interstellar, right? So he worked with Wheeler. They wrote a famous book on gravitation. And Wheeler very much believed that in the end, information was everything. He famously coined the phrase "it's from bits," that he felt that everything was ultimately going to have to be looked at from the terms of information. So, that's still, I don't think that's been borne out, but it's still something that people talk about. Is information, is that the fundamental way we should look at the world in terms of information? Like not just information and communication, but just is that the way we need to come up with a theory of the universe based on just on information? So it's had a lot of applications, and
well, it's interesting. They do go hand in hand with the information that you get from combining particles with the LHC. I mean, nothing means anything unless you have those ones and zeros that are transmitted to those hundreds of thousands of computers, right?
Right. Yes. Well, that is the way we analyze it for sure. And that's, I mean, again, CERN, is at the forefront of how do we handle so much information? How can we compress it? One of the interesting things is right now is, even with everything that CERN has done, the amount of information that we're having to deal with, not only at CERN, which is also expanding, but everywhere else is a lot of people believe really going to exceed our capability of advancing in terms of the classical way we construct computers, in terms of our chips, our semiconductor chips and things like that. And so one of the
what chips?
Semiconductors, the silicon chips, the things that are in our computers now. Okay. Right? So we've gotten used to these things getting faster and more powerful, right? That every couple of years there's new generations. This was famously canonized in something called Moore's law. And Moore's law was this observation that Moore observed, that it seemed like our abilities to make smaller and smaller and denser chips of semiconductors, every year and a half would double our capacity. And that has been true for many, many years. And we had taken, we have, benefited from it as our devices get smaller and faster and things like that. But we are approaching physical limits. We're at the atomic level almost. And so, and we're generating more and more data, especially like in artificial intelligence and things like that, with these, so-called machine learning devices that are becoming so, more and more evident. It requires huge amounts of data. And so one of the things people are investigating is the idea of, can we make a quantum computer, a computer that operates at the quantum level? And so IBM has now formed a consortium with a number of people, including CERN. And so I talked to some of my friends at CERN, and they're very concerned about the fact, no pun intended, about the ability to deal with all this, and that, are they going to need, what is the future of computing that's going to allow them to deal with all of this? And so again, information. That's our.
Can you explain in dummy terms for me exactly what the most fundamental basis of what a quantum computer is?
Yeah, so I mean, classical computers are based on, I mean, essentially a computer is based on something that has two states, a binary state, right? I'm going back to Shannon, actually, really. So, whether it's on or off, that you can store information. You can, if you change everything to zeros and ones,
Yeah.
and you can have an array of circuits that are on or off, and you can have an open correspond to, a zero, a closed correspond to a one. So you could, think about that. You can arrange circuits that would, basically be in a state of the zeros and ones, right?
Right.
That would, encode information. But with what we know is that at the quantum level, quantum mechanical objects, they can exist in different states at the same time. So basically, this is the strange thing about quantum mechanics, that the quantum mechanics, and it's something where, yes, you raised your eyebrows, and it's just like,
You're
yes,
starting to melt my brain here.
okay, what does that mean? And it's hard to comprehend because our brain, it is hard to think about what does that mean. But I'll give you an example. The simplest example, or one of the best I've seen, is if you think about a coin. So a coin can be, up or down.
Mm-hmm.
Okay, so
Heads
a
or
coin
tails?
is heads or tails. A coin is heads or tails. And that sort of, corresponds to a classical, chip, basically a bit. Okay, that it can be one or the other, just like an electronic switch could be on or off. But what if I spin the coin and I say, well, what is it, a heads or a tail when it's spinning?
Well, yeah, I mean, it technically has the little tiny edge around.
It has the edge, but exactly. But it's it's really in both states at that point, right?
Right.
Until it falls, and that is essentially a parallel to the way we think nature works. That nature is not in fixed states at the quantum level. When we observe them, we see one state or the other. But in the interim period, it is in both. And so if you think of, a classical computer, everything is fixed. Everything is, it's either on switch or off switch. And so that is, so a single switch can have two possibilities. It can be open or closed.
Yeah, I can open a window or a program on my laptop, use it, edit a video on it, or shut it down, and it's right.
Yeah, but this is even more basic than that. Is just, what do you do when you open a program? It's going in there, and there are physical electronics that are either the current is going through here where there's a one, or it's not going through here, or zero.
Okay.
And just think of everything as a sequence of zeros and ones, right? Just everything, every instruction, every piece of information. The color red is this is this. The letter A. Just think about how we code a letter. We come up with we have a there's a certain accepted string of zeros and ones that corresponds to A.
Okay.
A different one that corresponds to B, everything. So everything has a certain code to it. Okay. But in a computer, those zeros and ones, each one of them is a circuit, a switch that's on or off.
Okay.
Okay. And so each one of those switches is either just one or two things. But a quantum object, something that is actually behaving at a quantum mechanical level, a switch is much too big for quantum mechanics to be effect. It's a big thing. It's not just an atom. But an atom itself, or an electron, or something like that, it's in a quantum mechanical state. It's like the spinning coin. And so it can be both at the same time. So, unlike in a classical computer where a switch is it's either open or closed.
Okay.
An atom or an electron is spinning, and it could be either up or down or in between. And so intrinsically, it can hold more information than this thing that's just up or down, right? The spinning coin can intrinsically be including both information at the same time.
Just depending on how you're looking at it?
Yeah.
Okay.
It depends on how you will look. It depends on what you do to actually look at it at the end. So if you can put in, you can basically, whereas in the switch, you can only either say it's either 0 or 1. In that atom, you can say it's both at the same time. And then the trick is, how do you get how do you observe it and see what is the thing that you want? So,
Okay. So
the idea
go ahead.
the idea with the quantum computer is that if we can make components that actually operate quantum mechanically, there's a potential for storing a huge amount of information, much greater amount of information at the same time than you could in the with just a classical computer with chips.
Okay. So the main advantage to a quantum computer is just storing way more information.
Way more information, and being able to do calculations that are much more complex than you could ever do with the classical one, because it would just take forever to do the classical one. So things that would basically take forever, literally for as long as the universe has existed, there might be a possibility to do it with a quantum, because it can just operate with so much more capacity and simultaneously. So
like, for example, if we're talking about something like virtual reality or augmented reality, something this is done with a traditional computer with the same type of information, ones and zeros. So if you could imagine something like augmented reality on steroids, like times a million.
More than a million, even. Yeah.
Really?
Yeah. So I mean, things that we think would take, it's a completely different level of magnitude. But the problem is, they're very hard to do. So there are quantum computers now, but they are very limited in what they can do, because one of the problems is, how do you manipulate things at that scale? And they're very unstable. When you're dealing with atoms, as soon as you perturb them, they fall apart, or they lose their orientation. So generally, they have to be done at super cooled temperatures, so that there's no heat impacting it and things like that. And so it's still, it's another controversial thing. It's again one of these things. At this point, it's incredibly fascinating and theoretically intriguing, but there is debate in the field. Is this, like the LHC, in a sense, is quantum computing, is it going to be practical?
Well, I mean, it isn't a huge question also, is how our biological organisms like us going to be able to interact with it if it can store and quantify this massive amount of data. How can monkeys like us interact with it in a meaningful way, just like an iPhone, like these amazing devices? We only have our two thumbs. We can only do so much with an iPhone. So like the input output with a human being, like we can type with our fingers on a keyboard. There's only so much that we can do to interact with these computers. So like, isn't one of the big questions, how are we going to be able to integrate with them to be able to do or learn anything meaningful?
Well, yes, but we do that through a regular computer. So as I say, there are quantum computers that exist. In fact, IBM has made one available to anybody. They've put it, you can access it, if you go on the web and you look up IBM Q system, they have set it up and you interact with it like a regular computer. So the point of quantum computers is that the input and the output are regular computers. So we interact with them. So, your point is a very good point, is that the way we interact with them is classically, because that's the way we interact with things. So the input is classical information. So you're on a regular computer and you're writing a program. Now, what those programs look like, that's one of the big challenges, is what is the language to use for quantum computing? But there are people that are working on that. And as I say, there's online now. You can go online and there's a whole thing about, play with a quantum computer. And it's, the idea of IBM is they want to try to get people engaged and start to explore what they can do. But you go on and you write, you can program something and it sends bits, it sends zeros and ones to the quantum computer, down to these, whatever the system is. There's many quantum systems you can use. And it sends it down there and it encodes the information in a quantum system. And then you have to get that out of the quantum system and then translate it back into your classical computer.
Does that take the fun away from it though?
What fun?
I mean, doesn't that take like interacting with a quantum computer? I mean, there's a 2D or a regular binary buffer between you and the quantum computer. Like, wouldn't it be cool if you could just somehow directly interface with the quantum computer and eliminate all of the barriers that our biological bodies inhibit us from?
Well, it's not so much the biological bodies. Well, except that, look, we are entities that interact with our world through our senses. So at some level, you have to interact with physical things. The fact is, quantum, we can't possibly imagine, we don't have the ability to pick up an atom, right?
Right.
So at some level, you need something that actually interacts with the atom, and it's certainly nothing that we ever could do. We can't pick an atom up and move it. We can do it with a lot of devices, and they do. In fact, we can move atoms now, actually. I mean, we can actually move them around, but, not with our hands. We have these huge electron microscopes and, scanning tunneling microscopes that can, actually, they're enormous machines to interact with something at a quantum level. So at some level, you have to have machines that are doing it. And we just have to have, because of our physical limitations, we have to interact with a machine that can do it. We can't. I don't think there's ever any hope that we're going to actually be able to. What's going to change? You can't move an atom with your fingers.
Right.
No matter how good a surgeon you are.
Right.
So you need equipment to do it. We are dependent on tools at that level. I mean, it is an interesting philosophical question, is in a sense, at the quantum level, we know it through the tools. We know the world at the fundamental level. At CERN too, it's not like anybody ever really sees in a classical sense, with light, a Higgs boson. Mm-hmm. It's all many steps
measured,
removed.
Right?
It's all measured from these devices that we've come up with, our tools. Our tools, the way we understand the universe is basically through whatever tools we use to observe it. And so, at the macroscopic level, we have our eyes, and there's some perception of it, but our picture of the universe is based on our biology of how we see things. But as soon as we get beyond things that we can see, then it's based on the data and tools that we have and the picture that we draw from that. Right. I mean, we will never, what does an atom look like? It's based on something that these machines give us an answer to, a picture of. So there's that abstraction of, the way the universe looks is based on the way we look at it, whatever tools we have. If a tool looks at it this way and it can detect this part of it, then we construct an image of it from that.
Didn't we recently actually get like an image from a telescope of a black hole?
Yeah, multiple telescopes. Yeah, I mean.
So we have an idea of what it could look like.
Yeah, it looks like a black hole with a ring around it. No, it does. It was very exciting. I mean, it was, and again, it was, but again, telescope, it's an abstraction. It's looking at electromagnetic radiation, these big radio telescopes that are looking, and it was basically done by using multiple ones all around the Earth.
Right.
So yes, but it is true, and again, it's another example where we've created this image, but it's based on, I mean, these things that look like radar dishes and telescopes. I mean, they're gaining all this data, and then they combined it all, in very sophisticated ways to make a composite image of a black hole, which was, it's very exciting to actually see, what this looks like. And, the hope is that we can study it and study the, what happens around the perimeter and things like that. So, look, I mean, the idea of a black hole was initially just an anomaly. I mean, it was in Einstein's theory of general relativity that there was this problem that it predicted these things where everything blew up, basically. And for a long time, it just was regarded as a mathematical anomaly. And then, people began to think, well, actually, maybe can we study these things? Maybe it's not just something where the math falls apart. Maybe we can actually learn something about these mathematically. And eventually people did begin to figure things out about it. And now we think we predicted that they were existing, and now we've seen one, so first it was just, we could see that there was evidence of one, as I talked about before. You could see things rotating around something that was black, and it was so heavy that you had to think it might be a black hole. But now with this new thing the image that you've seen, you actually see it,
That's amazing.
Yeah, it's amazing.
Well, look, man, I really appreciate you you giving me your time. We just did 2 hours of fascinating conversation, and I hope we can do it. I could sit here for 10 hours and talk to you about this stuff. It blows my mind, some of these concepts and ideas. Tell people who are listening where they can find out more about what you're doing with your filmmaking and the other stuff that you're creating.
Yes, so Particle Fever, which is the film about the discovery of the Higgs boson, that's pretty widely available now. It's on Amazon, iTunes, Curiosity Stream, many places. And the bit player about Claude Shannon and information theory is now on Amazon Prime and on Curiosity Stream. And another project I'm working on now is an adaptation of Richard Powers' book, The Goldbug Variations. And so that'll be a fiction film, and it's looking at overlaps in music and biology and molecular biology, and again, exploring this idea of what is the best way to look at the world and to live in it. So
when do you plan on releasing that one?
Well, I'm got to shoot it first, so it's a script right now. Yes, so.
Well, awesome, man.
Good.
I really appreciate your time, and it was great meeting you, Mark.
Great. Well, it was a pleasure, and I hope that answered some of your questions, and that some of your listeners will be intrigued as well.